Creatine does not come from animals, plants, or fermentation. It is synthesized chemically through a reaction between two organic compounds, controlled in a reactor under specific temperature and pressure conditions, and then purified through several downstream processing steps. Understanding this process contextualizes the quality variation in creatine products and explains why manufacturing source matters as much as it does. The starting materials are sarcosine, also called N-methylglycine, a naturally occurring amino acid derivative, and cyanamide, a simple organic compound. In the synthesis reaction, sarcosine and cyanamide are combined in aqueous solution under controlled temperature, typically between 50 and 100 degrees Celsius, and the reaction produces creatine as the primary product. The yield and purity of the product depend on the precise temperature profile, the concentration and purity of the starting materials, the reaction time, and the pH management throughout the process. Byproducts form alongside the desired creatine. Dicyandiamide, as a dimer of cyanamide, appears when reaction conditions are not optimized. Dihydrotriazine compounds form through secondary reactions. Creatinine, the inactive metabolite, can form in the reaction vessel if conditions favor cyclisation. The amounts of each byproduct present in the crude product depend directly on how carefully the reaction conditions are controlled. After synthesis, the crude creatine undergoes purification. Filtration removes insoluble byproducts and reaction debris. Recrystallization, dissolving the crude product in hot water, then cooling to precipitate pure creatine crystals, is the primary purification step. The solubility difference between creatine and many of its byproducts allows selective crystallization of the desired product. Multiple recrystallization cycles produce progressively higher purity. Alzchem Trostberg, the German manufacturer behind Creapure, operates this process under pharmaceutical manufacturing standards. With extensive in-process quality control, validated analytical methods, and documented procedures at each step, Chinese manufacturers producing generic creatine monohydrate vary significantly. The best operate at comparable quality standards. Others optimize for cost by reducing purification cycles, accepting higher byproduct levels in the final product. The finished product is spray-dried or otherwise dried to produce the powder that enters supplement tubs. Particle size during drying affects the texture of the final product, the basis for micronized creatine. Quality testing of the dried product includes purity assay by high-performance liquid chromatography, moisture content, heavy metal screening, microbiological testing, and specific tests for the known synthesis byproducts. What this process tells you, creatine quality is determined at synthesis and purification, not at the blending or packaging stage. A supplement brand that purchases low-purity bulk creatine cannot improve its purity through packaging, flavoring, or marketing. The quality of what is in the tub is fixed by the decisions made at the manufacturing facility. The environmental and supply chain aspects of creatine manufacturing are increasingly relevant as the supplement industry faces scrutiny on sustainability. Creatine synthesis uses sarcosine and cyanamide as starting materials. Sarcosine is produced industrially from chloroacetic acid and methylamine. Cyanamide is synthesized from calcium cyanamide, itself derived from calcium carbide and nitrogen. These are industrial chemistry inputs with their own environmental footprints. German manufacturers like Alzchem have invested in capturing and recycling reaction byproducts and solvent streams, reducing the environmental impact of production relative to less tightly controlled operations. The pharmaceutical manufacturing standards that apply to high-quality creatine facilities impose waste handling and emissions requirements that lower-tier facilities may not meet. The choice between German and Chinese-sourced creatine is therefore not only a quality choice but potentially an environmental one. Though the full life cycle analysis depends on transportation distances, energy sources at each facility, and the specific waste management practices in place, none of which are typically disclosed in supplement labeling. Drying and milling are the final manufacturing steps that create the powder product. Spray drying produces a fine particle distribution. Fluid bed drying produces different particle characteristics. The drying process affects moisture content. Residual moisture above certain thresholds can cause clumping and accelerate degradation during storage. Packaging in moisture barrier containers with desiccants addresses this for most supplement grades of creatine.